Okay? So now this will be recorded. Okay, so today we are going to talk about trees in general, actually. Before we even get to binary trees, just trees. Okay? So, you have seen a form of a tree before. Technically, linked lists are trees. They're just single branch trees. However, a more interesting usage of them is a binary tree. So let me just quickly show you a binary tree, and then we will define a couple of terms. But this is what you typically see when you see a tree. You have these nodes that are connected to other nodes. That's a linked list. However, just like, remember like with big O, when I say something O(n) squared, that can belong to O(n) cubed, technically. I mean, that's like selling your car short, right? That's like saying, yeah, my car can only go up to 20 miles per hour, even though it can go 100. Yeah, sure, you can say it can go up to 20. That's technically correct as well. But, you know, you want to say this instead of this, right? Same thing with a binary tree. With a binary tree, it doesn't have to have, as the name implies, two branches, so two children here. It can have one or none. Okay? So let's just go ahead and start defining a couple of these terms that I'm saying. Trees are what we call hierarchical. I think. Is that how you pronounce that? Hierarchical? Try pronouncing that. Hierarchical. Whatever it is. That's why I wrote it. Make Google play it for you and pronounce it. So that word, which means hierarchy, data structures. So when you think about a hierarchy, you're thinking about like, well, military people, hierarchy is like your boss, higher rank, right? Up in the branch or whatever, right? So yes, all the trees typically have something that is known as the root. So say it. Give me your phone. Put it close to the recording.
Hierarchical.
There you go. Well, yeah, we might have to upload this one. So okay. So yeah. So most trees typically have a root. And a root of a tree is going to be sort of your initial node. If you think of a linked list, that would be your head. Now, each of these nodes, so we also call each of these circles nodes, or what's another name for them? What?
Internal vertices.
That's more of a graph term. This is specific. I mean, yes, this is a graph ultimately, but we haven't gotten into talking about true graphs, so I think that'll confuse you a little bit. I think let's just stick to the word node. So these are nodes. These are all the circles you see here are nodes. And then, yes, if you're talking from a graph point of view, this is a vertices and this is an edge. But, we haven't gotten quite there yet. And each of these nodes is connected from anywhere from 0 to 2 children. So what's a child? What? Yeah, okay. So a child is a node that is connected to a parent node. And it's higher in the hierarchy of things. So for example, if we have just these three nodes right here, we would consider this to be the parent, and we would consider both of these to be the child or children of that parent. So you can think of like a family tree. This is dad, or it could be mom, and then this is kid 1, kid 2. Original names. And so it'll be a little bit weird because you don't have a mom, so single dad here. But yeah, think of it that way for now, okay? Furthermore, when you're building trees, if it's something like a unary tree, we have a root, which also happens to be the parent of this guy. And technically, is also the grandparent, although we don't really use that term of this node. Okay? We don't really say grandparent though. We stick with the word parent and child. This, on the other side, is a child of that guy. And then this guy is a child of that. And I suppose you could technically call it the grandchild of the original, right? As well. But we don't really use, again, grandparent or grandchild. But, I guess you could potentially. Furthermore, when you get all the way to the bottom of your tree, and by that I'm saying when there's no more branches or no more nodes beneath you, so like here we have a tree, and then these don't have any children coming out of them. So when a node has no children, we call that a specific way. We call that a leaf node. So these would be considered a leaf node, or plural of that, leaves. So again, the topmost node is called the root of the tree, and the elements or nodes that are directly under a parent node are called children. So anything directly above something is called a parent. So for example, if we put an example like with letters here, we can say that A is a child of F, or like H is a child of F. We can say that K is a child of J. We can say that K is the parent of Z. Okay? And then we can say that A's, H, and Z are leaf nodes. Leaf nodes, okay? So, why would we use trees? Well, one of the reasons to use trees is when you want to store information that is naturally in the form of hierarchy. One example of that is a file system in the computer, right? You have a folder, and inside of that folder, you may have multiple folders, right? So like maybe this is your home directory in Bobby or Sally. And then there you have a CS202 folder, and inside of that you have the Inception assignment that you guys did. What was number 16 or something? I don't know, 17? 13? Really? We only had 13 assignments?
You had 14.
Wow. Okay. Thought we had more than that. Don't worry, we'll have more in this class. And then on this here we could have 302. And then in there we would have maybe the Qception. But you may also have a Star Wars section, I guess. And from there you have assignments 1, 3, 5, and then probably like 2 more we'll have. Yeah, so this will probably be like 8 and I think 10. And I think the final project may be Star Wars related too. So this, of course, is not a binary tree actually, because if I draw this in a not messy way, first of all, you probably have 13 nodes here, right? And similarly here, you have like at least 2, 4, 6. 2, 4, 6. And you might have more here as well. So whatever the node with the most children is, that's going to define what you call your tree. So if any node in the tree has more than 2 kids, so if it has 3 at some point, then this is no longer a binary tree. It would be a ternary tree. Okay, and so on, whatever the terminology is for 4 and 5 and so on. Yeah. What's that?
I thought what you said, like 4 and then airy tree, like 5 tree.
I mean, you could.
You could. I mean, that's the graph theory Eclipse notation.
Sure.
They're just like,
Okay, I believe you. So that's one usage of them. From there, we can order trees in specific manners, such as a binary search tree, in which case, when we're searching for something, it may be sort of a decision, like whether you go left or right based on something. So for example, suppose that we're trying to sort a couple of letters. We have M here. And anything on this side will be less than M, or equal to M. Anything on this side will be greater than M. So in this case, for example, here I could put the letter G. Over here, I could put the letter T, right? Because G is less than M, and T is greater than M. Down here, however, I could put A, and I could put L. What I couldn't put here, because it would violate my binary search tree, would be anything greater than M. Because, yes, here, technically, I just have to put something that's less than or equal to G. But for this side here, I have to put something that is greater than G, but less than M. So I'll just call that, I'll just say node. So here, let me write that. So G is less than my node, which is less than M, like that, okay? And here the node would be less than or equal to G. So what letters could go here? Well, what goes after G? H, I, J, K, L, and then that's it, because M is here. Actually, I could also have M's, technically, because I have duplicates, right? So M could go there as well, but nothing higher than M. So less than or equal to, probably a better solution for that, for duplicates. And so you have to maintain that, because if I'm looking to see, and let me finish filling this. Let's put this as an N, and let's put this as a Z. Suppose that I'm looking to see what letters I have. All I got to do is ask the question, is the letter I'm looking for greater than or less than M? And then suppose that I am looking for the letter A. Well, that happens to be less than M. And then the next question I ask is the letter greater than or less than G? Well, A is less than G, so I'm looking to that. And voila, I have found A. Suppose I'm looking for the letter U. Well, is U greater than M? Yes. Is U greater than T? Yes. Is U greater than Z or less than Z? Well, it's less than Z. However, Z has no children because it's a leaf node. Therefore, we can say that the letter U is not found in our binary search tree. It turns out that searching for something in a balanced binary search tree is O of log n, as long as it's a balanced binary search tree. What balance is and how to achieve it is a pathway with many abilities. It's ABL trees, which we'll get to. So it's not just something you can just magically come up with. So a binary search tree can provide quicker access to information in terms of accessing and searching. However, let me provide you an example of a binary search tree that is going to lose this advantage and still be n time to search something. Because remember, a linked list takes n time, right? To search a number in a linked list? Yeah, even if it's a sorted linked list. I could rewrite that same tree that I have up here as follows. Typically, you don't have to, but it makes more sense to look at it. You want to keep your children beneath your parent as you're drawing the tree, because if you do what I did up here like this, it can be a little bit confusing for people. So you want to do something like that or like that. So, but of course, sometimes space is a concern. So, try to zoom out a little bit. Yeah, okay, so these two trees have the same number of nodes. They each have 2, 4, 6, 7. and they have the same nodes actually, the same letters. However, and both of them are technically can be considered binary search trees. Although technically, the one in the bottom has a special name, it's a degenerate tree. Yes, this is the official term. And it's called a degenerate tree because it essentially becomes a linked list. There's no binary to it. They're all literally unary connections, one child each. And now, searching for the letter U means that I have to potentially go all the way to the T before I can tell you that U isn't found. Actually, no, because U is after T, so actually I go all the way to the Z. Once I get to the Z, then I'm like, oh, I passed it, okay? So, yeah, searching through this will take n time, and you will lose the efficiency of your binary search tree. So just because you have a binary search tree doesn't mean that you can achieve log n time. That's where the word balance comes in. If you have a binary search tree that's balanced, then you can say that you can search in O log of n time. Again, achieving that is not easy. Use ABL trees or other methods, which we will talk to probably next week. In addition to that, let's talk about insertion and deletion. Trees provide moderate insertion deletion that's quicker than arrays because it's a linked list essentially, right? Like, in the form of a linked list where you're dealing with pointers, where you can just move pointers around and put memory and stuff. Because, okay, suppose that I have the following binary tree in my computer. Well, what really this will look like is somewhere in here I have the root node. So we'll call this root, and then we'll just call this like some nodes. And then here is as a pointer. So maybe I have something like a head pointer that points to that first thing, okay? So here, all I have is a pointer that points to like 400 or something. And then 400, just like a linked list, it's actually gonna get a little bit trickier, right? Because let's talk about that. So a linked list has two components, right? Or it might have more than that if it's a double linked list. But a singly linked list has two components. What are those components? Data and link. Or next, or whatever you want to call it. A binary tree will be kind of like a double linked list in the sense that it's going to have the data and it's going to have two links. However, in this case, the links are known as the left and the right child. So for example, if we're looking at M, it will have a link to G and to T. So this would be like M, and then this will be a pointer to G and a pointer to T, right? So from an implementation perspective, if this is our head pointer here, and that points to address 400, and address 404, and address 408, this is hex though, then maybe here's the data component, which would be, in this case, R. And then the left here would be just an address. And then the right would be another address. So somewhere here is address 200. And then here we have the letter A. And then technically you have two more spots, but they are null. Because similar to the to your linked list, when you have a linked list and that node at the end is not pointing to anything, you set it to null, right? In a binary tree, when you have a node that is a leaf node or a node that doesn't have two children, it just has one, such as the example of W, then you just make those pointers to null. Make sense? That's just strictly from an implementation perspective. But yeah, in memory, these are all over the place. So it only looks nice when you're drawing it. So because of that, you can quickly change a pointer and just throw in things out of order. I'm going to say out of order is you don't have to shift things around to be able to insert a child node. And so you have quicker insertion and deletion in an array. However, you could say that it's a slower insertion deletion than an unsorted linked list, because that one you just throw in a tail or head. But I mean, you could just also have a tail or head somewhere. Have a tail somewhere here where you just keep dumping things in the next spot and make a degenerate tree. So basically, because similar to linked list, and unlike arrays, you can keep inserting as many things as you want to these binary trees or ternary trees or any tree. You can just keep dumping things inside, and as long as you don't run out of physical memory, then random access memory, then you're okay. Unlike an array where you have to set a size, right? Even if it's a vector, you don't set the size, but internally the thing will resize eventually. So here you don't have to worry about that. So what applications do we have for trees other than information like a file system? One of the big advantages of this is making data quicker to search. So right now, the fastest thing that you've known is an array version of the data with binary search, which I briefly went. I think I barely touched it, right, one day? Did I? I might have done two. This moved into one class out of 3 I didn't do.
I don't remember.
Mm-hmm. Well,
I think you might have discussed it.
Yeah, binary searches were like you have a book, you open it in half, you look at that, and then you look at the next one. Okay, there we go. Yeah, so that's binary search. That's log n time as long as the list is sorted. This tree stuff is very, very similar to that. The way that this is set up is every time you open it by half is one of those nodes, basically. And you split it, and you split it, and you split it. So that's where, if it's a balanced tree, we'll be opening it by half. If it's the degenerate tree, it's like opening the first page, then the second page, and the third page. So basically, trees make information easy to search. Of course, you can manipulate hierarchies. So like, suppose you get a rank up, you get a raise or whatever, then you can just move up in the tree and so on. You can manipulate sorted data very easily. So for example, G, A, and L, that's sorted within its own subtree, right? You can get rid of that as a whole, or you can put that somewhere else.
But if a node ranks up, then what about all the child?
You bring them along. Yeah, everything's hooked up along. Yes. When we get to rotations in ABL trees, you will see that. Yeah. So it's also very useful for composing visual effects and digital images, for example. Each of these could be a layer of a picture. And routing algorithms use trees all the time. And anything that has to do with like decision trees. So when you have something like chess, where you have to make decisions, you could make a massive tree. In fact, you run out of memory doing that tree for all the possibilities. Where each, like for example, that's the beginning of the game. And each child is a possible move. And from that move, you can make other moves, right? So then your tree's gonna grow super wide, right? Because all the possibilities will change, right? People have built trees like this, I think, for checkers. For chess, it's too big to put in a computer. So the possibilities are like really, really big numbers. And we'll talk about that in a second when we talk about some of the properties, such as how many nodes each level will have. So ultimately, a binary tree is just going to be a tree whose elements have at most 2 children. And since each element in the binary tree can have only 2 children, we typically name them left and right, which I already talked about. And so, from an implementation perspective, like I said, it's going to be very much what you've done already. So we could have something like a data int data or data pointer, It could be a pointer to data, kind of how you're doing in your assignment. And then you could just have a node pointer left and node pointer right. And you want to initialize these to null in your constructor, okay? In fact, I could probably do that here if I use C++11, right? Okay, so moving on, let's talk about some interesting properties that trees have, because I think that makes us understand them better. Let me check to make sure this is still recording. Yep, okay. So, here I have 5 properties that we can talk about. And I suppose let's just put a random tree here. Binary tree. so that we can refer to it. Okay? In fact, one of the things that we already heard is the word balance, right? What does it mean for a tree to be balanced? Well,
Is it like all the amount of children is the same, so it's always going to have like 2 children if it's a binary tree?
no, not quite. It turns out that the word balance is kind of algorithm specific. So an ABL tree has a very specific definition of what a balanced tree is versus something like a red-black tree. So typically, yes, it should look sort of balanced in the sense that if I was holding it with a string, it wouldn't tilt one way or the other, you know, it would be like the scales of justice style thing. But for example, I could say that this is actually a balanced tree. And the way it turns out is that we can compute that, for example, by saying how many children does this have? And because this has no children, then we can say that this has one children here and no children here. And then this has 2 children, technically. And then over here, we can say this has nothing, 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 nothing. This has 1 and 1. And so therefore, this comes as 2 now. Now you see this is a 2, right? Not a 3. That's just building it based on this number here. So it's kind of a weird notation, which we'll talk about when we get to ABL trees. So this will be considered a balanced tree, actually. The big difference is the number on the left and the number on the right cannot vary by more than 1. That's going to be your rule. We'll talk about it. We'll spend the whole class period on that. But ultimately here, this is balanced. How to make it unbalanced? Well, now it's unbalanced. Because if we do the same notation, 0, 0, 1, 0, 2, 0, 3, 0, 0, 0, 0, 1, 1, 2. These are okay, this is 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 not okay, because the difference between the left and the right is more than 1. Solution, you make a rotation. And
Could you explain how you got the 2 on the right side for the top tree?
this 2? This 2?
No.
This one?
No, the top, very top one. 'Cause you have
This one?
No, the right one.
This one.
Yeah.
Okay. So
Yes, because you have 0, 1, and 0, 0.
every time you go up a level, you add 1 to the biggest number that you have. So here the biggest number is 0. Here the biggest number is 1. Therefore you get a 2. Here the biggest number is 0, so you get a 1 here. Here the biggest number between these two is just 1, so you get a 2. If you had another node here, it would be a 3. Like I said, when we talk about ABL trees, I'll write the algorithm, but it's rather simple once you see it. So, anyways, and then you make if this is considered unbalanced right here, and then you would make a rotation where it's kind of hard, but you basically cut off that, and then it's like you pull this up, and then this guy comes down. So like it swings here. I think I can try to do this. Let's try. Yeah, so it swings down like, whoa, like that, okay? And then you have the child there. And that's how we got that, okay? That's a rotation, that's ABL trees, that's in your future. But not now. I love ABL trees, favorite thing. Yeah, so, okay. So balance is a special word, but before there, let's talk about other sort of nice terms. So I'm gonna write a couple of properties here. So these are binary tree properties. First thing, let me just write it. Okay, the maximum number of nodes at level L of a binary tree is 2 to the L minus 1. So here, Level is the number of nodes on a path from root to the node, including the root and node. And we consider the level of the root to be 1. Okay? So if we have our binary tree here, we are saying that the root is level 1. And be careful, because sometimes in some algorithms we consider the root to be level 0. So that's just strictly a algorithm specific. But for now we're saying the root is level 1. That means that this will be considered level 2, level 3. And by that I'm saying that's level 2, and that's level 3. And here, that's level 1, okay? If we had a node here, that would be part of level 3. But we don't. So the property is saying that based on this level notation, the maximum number of nodes that we can have at a certain level is 2 to the L minus 1. So let's look at level 2. So we're saying that at level 2, so if L is equal to 2, the most amount of nodes that we can have in our tree is 2 to the 2 minus 1, which is 2 to the 1, which is just 2, which happens to be the case because we only have 2 nodes there, right? What about level 3? Level 3 would be 2 to the 3 minus 1, which is equal to 2 squared, which is equal to just 4. The maximum number of nodes at this level is 4. Is that true? We have 3 nodes here, but we have 1 spot available. So yeah, that's true. Okay, what about if L is equal to 4? That's 2 to the 4 minus 1, which is just 2 to the 3, which is 8. Okay, let's try it. Each of these can have up to 2 because it's a binary tree, right? So 1, 2, 3, 4, and then 5, 6. And then if we had our imaginary node here that was full, 7, 8. So it's correct, right? This can be proven by induction. So right now I showed you kind of like, yeah, it makes sense that that this is right. But if you want to have like the mathematical proof, you can prove it by induction. You want me to prove it? All right, we'll prove it. For root, where L is equal to 1, the number of nodes is equal to 1 minus 1, which is equal to 1. Okay, that's the first step of induction. Induction is a 3-step process. The second step of that is to assume, that's your assumption, your hypothesis, whatever you call it in induction. Assume that the maximum number of nodes on level 1, or sorry, at level L, not 1, is 2 to the L minus 1. And that assumption is like what we set up here. So since in binary trees, every node has at most 2 children, because that's why it's called a binary tree, the next level would have twice the number of nodes, which can be represented as 2 times 2 to the L minus 1. This 2 times would go up there, and therefore there's your proof. Now, math people can refute that if you want. Okay? Any questions about that? Yeah. Well, all right. So that's the first property. When can that be useful from the implementation perspective? Well, suppose somebody told you, I think our tree that we're making can grow up to 15 levels. and I was to ask you, at that height, height's another term I should define. At that point or height, how much memory space do we need to hold that level? And let's say that each of those nodes takes 10 bytes for some reason. Then you can calculate that using this, because you can do 2 to the L minus 1, 2 to the 15 minus 1, so 2 to the 14, whatever that number is, and then multiply it times the number of bytes for each node, and now you know. So it can be useful. What is the height of a tree? Okay, height is going to be the, so let me define that actually. That's another useful term. So height is the maximum number of nodes. Zoom that in a little bit. En route to leaf path. So the height of the tree is going to be the longest path that you can find in the tree from the root to the leaves. So for example, if we look at, let's just make another tree. That's technically a binary tree. And you can see that because you got this one guy, at least it has 2 here. But either way, I'm claiming it to be a binary tree, therefore it is now. So the height of this tree is going to be the longest path you can find from the root, which is going to be this guy, because this guy is going through 1, 2, 3 nodes. Over here, you're only going through. So this is what we're going to consider to be the height of the tree, because it's the longest possible path that you can find. And by levels, that's level 1, 2, 3, and 4, technically. That's level 4. So this has 4 levels.
You don't go from 0.
You can if you want. That's what I'm saying. If you consider level to be 0, then changes. But I mean, that would messes up our little nice equation here that we have.
Yeah.
But yeah, sure. So the height of a tree with a single node also. Technically, I haven't said this, so this is actually good. That single node is considered a tree. And in fact, I call that a 5 tree, five nary tree or whatever.
Call that a 1,000 tree.
What?
You can call that 1,000.
Yeah, you can. I can call it whatever I want. And so that's a very special case of a tree. And we consider the height of this tree to just be 1. And that result can be derived from the certain following property of a tree. So it's going to be the second property that I'm going to write here. The maximum, I haven't written this right now, I haven't. Okay. Number of nodes in a binary, not search, sorry. It could be search, but I'm generalizing more into just any binary tree of height h is 2h minus 1. Okay? So now I have a difference between height and level. And you can do the same derivation that you did above with the induction. So a tree has a maximum nodes if all levels have maximum nodes. So maximum number of nodes in the binary tree of height h is 1 plus 2 plus 4 plus 8 and so on plus 2 to the h minus 1, which is a simple geometric series with h terms. And the sum of this series is 2 to the h minus 1. Now, it's possible that, yes, in some books, height sometimes of a single, of a leaf is just considered to be 0. If you want to use that convention, then you can modify this to become that. Okay? If height of a single node is 0. Okay, so that's if you want to make your height of a single node. Okay, so because some books do use that. So, but so, I mean, look, this looks much nicer, right? So just go with that one and the subtraction stuff, the you do +1 and nasty stuff. So, yeah. Okay, next property. I don't like that the emails are popping up there. Turn that off. Hopefully you guys remember what those things mean. Everybody remember what the floor and ceiling functions are? Who does not? Let's put it that way. You don't know?
Yeah, it's been a while.
Okay, so basically,
I never used it.
Yeah.
basically it's saying up but not including that number for ceiling, and for floor is like low but not including that number, I think as well. Is it? Or do you include? I don't think you do include also the floor function the number. So, yeah.
I remember as like upper and lower bound.
Yeah, kind of.
I don't remember exactly what it was.
So anyways, what this is saying is in a binary tree with n nodes, the minimum possible height or minimum number of levels is going to be the ceiling function of log n plus 1. But n is the number of nodes, basically. So if I tell you that a tree has 7 nodes, okay? What can you tell me about the minimum height? Because I mean, I could make it like this. I could make a degenerate tree again. 1, 2, 3, 4, 5, 6, 7. And we start at level 1, 2, 3, 4, 5, 6, 7. So that has 7 levels, right? And based on their height formula, if we're using the easy one like that, then this has, you know, lots of height, basically. So the minimum, though, that we can do from this is going to be that log n plus 1. So then I'm saying 7 plus 1, which is 8, and then take the log of that, which is 3. Is there a way that I can reorganize this into just making it 3 levels or 3 height? Yes. So all I got to do is basically, here, I'll number them. Put the 4 there, and I'm keeping, so now let's suppose I also put the same numbers here, and I'm keeping that same order. I can go ahead and put like a 2 here. 1, 3, 6, 5, 7. And now you have 1, 2, 3. Okay? So basically this is saying, how good can you go? How tight can you make this? And you can take that log to figure that out. And you know, so what happens here is if we consider the convention where the height of a leaf node is considered 0, then the above formula can change to this. So yet again, if you're like Sam and you want height to be 0 for the root node, then you gotta change it to something nasty.
Well, you think about the rectory and
No, I mean there's some cases where not gonna be kids,
the
but
root user
so
has 0.
this is the Sam section. All right. Okay. So what are we at? This is 3, right? So we got 2 more to go. I mean, these same notations I've been using. Well, that was L for what was I using? Levels. So no, then I don't want to use that notation. So I guess we'll use capital L then. So a binary tree with L leaves has at least log L plus 1 levels. So this is looking just make sure we understand that. Okay, how many leaf nodes? I'm going to number these. How many leaf nodes does tree 1 have? 2 nodes. This guy and this guy. How many leaf nodes does tree number 2 have? Yes, 1, 2, 3. Again, the rule is a leaf node has no children, basically. This guy has no child. This guy has no child. No child, no child, no child. So this has 3 leaves. What about number 3? 1. That's right. What about number 4? Okay, good. I just want to make sure we're all on the same page there. So now I'm saying a binary tree that has, so suppose you don't know how big the tree is, how many levels you have. Then, and I tell you, well, you don't know, you know, I'm looking at a tree. It's, you can't see what the tree's made of, but I tell you that it can only have, that my tree has 3, so like this one, it has 3 leaves. Then you can say at least in the best case scenario where the thing is really tight, it will have at least log L plus 1 levels. And that means log 3, oh gosh, plus 1. But ceiling function. So what's this going to be then? 2 plus 1, which is 3. So we're saying at least it'll have 3 levels. That is correct. How else could I have 3 leaf nodes and make it less than that? I can't. It's impossible to make something with 2 levels that has 3 leaf nodes. Think about it. There's only 2 nodes I could have in something with that level with the height 2, right? However, I could also make something bigger. I could do something like oh shoot, I don't know how I'm gonna get this now. Yeah, I kind of went too far here now. I don't know how I can make this up with 3 leaves now. There we go. This has technically 1, 2, 3, 4, right? So I'm saying the smallest that I can make it, at least it has three levels, but it can be more than that, as you can see by that example. Good on that? Cool. Finally, number 5. Like lax, it won't let me slide up. There we go. Okay, so in binary trees where every node has 0 or 2 children, the number of leaf nodes is always 1 more than nodes with 2 children. So, let's look at some of those trees up there. In this tree that we have here, how many nodes have less than 2 children? Or actually, how many nodes have 2 children, first of all? Looking at this tree. 2 of them. Nodes 1, well, let's name them actually. So this is 1, 2, 3, 4, 5, 6, 7, and 8. Nodes 1 and 5 have 2 children. How many nodes have one child only? 3. Let's see. This was not count, so 1, 2, 3. Correct. So that's nodes 2, 4, and 3. How many nodes have 0 children? 3 nodes, right? 6, 7, and 4. So this is saying in a binary tree where every node has 0 or 2 children, so this doesn't apply, but we can fix that by putting in a node there, right? So now then, no, we don't fix that either. Then we would have to put something here. We have to put something here. Now we're good, right? So this is good, this is good, this is good. Okay, now we're good. Okay. So in a binary tree where every node has 0 or 2 children, the number of leaf nodes is always 1 more than the nodes with 2 children. So let's see. Here we have now 1, 2, 3, 4, 5. So we have 5 nodes with 2 children. And we have 1, 2, 3, 4, 5, 6 nodes with no children. At least in that case, I prove, right? You can prove that on your own at home. I'll leave that as an exercise. But basically, it's saying that something where it's in this special case of a tree, that's a property that you can take advantage of. Now, why am I telling you all these properties? Well, these properties are going to be sort of our facts that we're going to use later on when I'm showing you some algorithms and why they actually work the way they do. And they're not going to be like, well, remember that the height of the tree for this number of nodes is this. Then you're going to be like, oh yeah, that's one of the things we showed you. Okay, well now we're going to take advantage of that when applying something like this X algorithm or Y algorithm. So that's why we spent time talking about that. Okay. Next category. Let's talk about the types of binary trees. So a couple of terminology based on what the tree looks like. First, let's use the full binary tree. A full binary tree, we consider that to be a binary tree is full if every node has 0 or 2 children. So is this example that we saw a full binary tree then? Yes, because remember, the only way we could show property 5 here was to make everything have 0 or 2 children, right? So we got rid of all the single child nodes. So technically that is considered a full binary tree. I know that's weird because you hear the word full and you're thinking it should have all children, but that's going to be complete. So that's why I'm going over the terminology, because it can be a little bit misleading. So let's just put a bunch of examples. So I guess the most basic example is a single node. That's a full binary tree because it has 0 children, or 2 children, in this case 0. This also it's a full binary tree because everything has 2 children or no children. That is also a full binary tree. what happened there. God damn, why I keep doing that? In fact, it's a general case. This is a full binary tree. That's a full binary tree as well. And you see that, how the pattern goes on that way? It doesn't look balanced, it doesn't look complete, but it's a full binary tree. Every node has 0 or 2 children. In a full binary tree, the number of leaf nodes is the number of eternal nodes plus 1. So I'm saying, how many leaf nodes does this tree have here? Wow. There we go. 1, 2, 3, 4, 5. 5 leaf nodes. So how many internal nodes does it have? 4. So those are our property stand. 4 plus 1 is 5, right? Other example here. How many internal nodes? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Therefore, there must be 12 leaf nodes. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're good. This is basically flipping around the property 5 from before. Some of these properties are just like the inverse of them or like log of them. So, proof of this, if you want to try it at home, is called the handshaking lemma and tree. So you can look that on your own time. Next term, complete. A complete binary tree, we consider a binary tree to be complete basically when all the levels are completely filled. But here's the big thing. Except, I guess the word possibly, the last level. However, that's a special case where, so I suppose the word and, the last level has all the nodes to the left, or as left as possible, I think is probably a better thing. This will come in use when we're talking about heaps, actually. So we consider a binary tree to be complete when all levels except maybe the last one is not full. So look at this right here. Every level is full here, so we're good, right? Or complete, so it's all good. Are filled. That's also a complete binary tree because the last level is not full. There's 2 spots empty, right? There's this spot and this spot. However, the spots that are filled up in the last level are all the way to the left. So this passes the test. However, this does not pass the test because the spots that are empty are on the left side. So, and then you have nodes afterwards. Is that complete or not? Yes, it is. Be confident about that. Yes, it is. Because this spot is empty, but this is the last level technically, and everything is to the left. Is this complete? No, it's not. Is that complete? No. How do I make it complete? Now we're good, right? If I put that, is that complete? Is that complete? 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 Is it complete now? What about that one? I made it ambiguous because I made it straight down. So, yeah. Yeah, I should do that. Just make it sweat. And since I'm not here, you can't even ask me. So then the TA is going to be like, how can I help you? And then be like,
But this is based off of the same thing as with recursion. We go down to the left and go to the top first. Yes?
Yeah, you can say it. When we get to traversals, yeah, I suppose so. That's the one way that you could code an algorithm to check whether something's complete or not. Okay. So, next ones. Let's do, yeah, we have time for one more. The perfect binary tree. A perfect binary tree is a tree in which all internal nodes have two children and all leaves are at the same level. So, remember, the internal ones are the ones that are not the leaf nodes. So this is like your country says, if you have kids, you must have two kids always. You can't have one kid. You have to have two kids. Two kids or no kids. If you have one kid, we have to kill him or you have to get pregnant again. So basically, two-child policy, I suppose. Yeah. So examples of that. That's good. Is that okay? Is that okay? No, because the leaf nodes are not at the same level. That's okay now. What about that one? Why? Why is it not okay? Yes, very good, very good, very good. Those are not at the same level. Right? All leaves have to be at the same level, and those are leaf nodes.
Yeah, those are at the same level as well. Yeah. Or,
So it's not perfect then.
okay.
So then,
Wait, what are you trying to do? These are the-
now we're good, right? They're still growing. They're still growing, okay? They're young. They're young. So you have 2 minutes. Okay, so next time we'll pick up and talk about balanced and then degenerate again, I suppose. All right. Thank you for watching the video. Like and subscribe. Yeah.